Alright, so in this example we have block C, which has a weight of mg, and we're told that the block is traveling with the speed of v0 when it strikes a fixed wall. We're told that a spring of stiffness k is attached to the front of the block and that the spring eventually contacts the wall, resulting in a maximum compression, delta max. Based on the information given, we're asked to determine the spring stiffness k. If you would, you can think of this as a classic bumper design problem on a car, and since we're looking at speeds and compressions, we know that this is probably going to be a work energy equation. In that regard, let's go ahead and sketch a free body diagram for the system. So if we treat it as a particle, we know that we're going to have the weight of the system, mg, we'll have the normal force n, and once we make contact, we'll also have the force due to the spring, which I'll call FSP. Now we know from experience and from our understanding of the work energy relationship that the normal force is not going to contribute any work, so I don't need to worry about that. The effect associated with mg in this problem is not going to be very impressive because we know that we can define a datum here at the midplane, and so we're not going to have any potential energy contributions. But if we wanted to include it, we could include it in the potential energy if we'd like. And of course we'll do the same with the force of the spring. So if I want to solve this using the work energy relationship, what I'll have is that T1 plus V1 plus the non-conservative work done moving from state 1 to state 2 is going to equal T2 plus V2. I can go ahead and start substituting in terms here. So if I do that, T1 is going to be the initial kinetic energy of the system. It's moving with a speed V0, so I'm going to have here 1/2 times m times V0 squared. Potential energy, you could count for mgh in each, but the way I've put my datum here, this is going to be 0. We know there's nothing in this problem which contributes non-conservative work, so I know the U1 to 2 non-conservative is going to be 0. At the point of max compression, the block will actually be changing direction, so it'll instantaneously have 0 velocity and 0 speed, so T2 will be 0. And then V2, the point of maximum compression, will simply be the amount of deflection in the spring, so this will be 1/2 times K times delta, I believe we call it delta max. Let me just go up to double check. I don't want to change the notation on you. Indeed, that's correct, delta max. So this is going to be delta max quantity squared. So I can go ahead and take these 5 terms and substitute them back into the work energy equation. And if I do that, I'm going to have that 1/2 times m times V0 squared. It's going to equal 1/2 times K times delta max quantity squared. So I can go ahead and solve this for K. And if I do so, I'll note first of all that the halves are going to cancel out. And so what I'll be left with here is that K is going to equal m times V0 squared divided by quantity delta max squared. From here you can plug in the numbers using the values that are given and you'll be good to go. Best of luck everybody. Take care.